Okay, well, uh, we will. I'm happy to have you here, Richard, and we'll do our lesson today. Okay, so today we're working in chapter 7, and here we are getting into the concepts behind hypothesis testing. Now, last week and the week before, we got into our first exposure to statistical inference, and that was through the confidence interval. And the confidence interval, with the confidence interval, what we started off with, we begin with a sample. And we look at the sample and we say, based on what we see in the sample, what does this tell us about the population? Okay, and we say, and we ask, okay, and so the premise there is that you've got this little sample, and the sample has a mean, y bar, and it has a standard deviation, s. And based on these two things, we create a confidence interval for mu, and mu is the population mean. Okay, and based on what we see, we can then ask questions like, does our sample provide evidence that the population mean is different from 55 or whatever it might be? Okay, so here's an example. Let's say you have a sample of, n equal to 10 things, and y bar is 45 and s is 3 or whatever it might be. Okay. Let me just change this up so n is 9. This will make my life a little bit easier. Okay. And so when you make a confidence interval, you have y bar plus or minus t star times s over the square root of n. So in this case, I have 45 plus or minus t star times 3 over the square root of 9, which is 3. And so I look up, let's say I want to do a 95% confidence interval. The value that I use would have 8 degrees of freedom, 2.306. Okay, so my t star, 8 degrees of freedom, 95% confidence, 2.306. And so my confidence interval ends up being 45 plus or minus 2.306 times 1. And so I get a confidence interval is essentially 45 plus or minus, I can just round off to 2.3, and so I get, I go from 42.7 to 47.3, whatever my sample population mean is. And so I would say, so this should all be review. I am 95% confident that mu is between 42.7, and 47.3. Okay, and so now someone can ask, well, do we have evidence that mu is not 48? Okay. Okay. And so, Richard, based on our confidence interval, what would your answer be?
No.
So we would say we do have evidence that mu is not 48, right?
Yes.
Yes, right. So we do have evidence that mu is not 48 because 48 is not between the interval. Exactly, is not between the ends of the interval. Okay, so that was our first thing about statistical inference, exposure to statistical inference, and that was through confidence intervals. Okay, and then we created confidence intervals for a difference between two means, etc., etc., etc. Okay, in hypothesis testing, we're going to do something similar, except here. Let me just say this: stats XL13. Except we don't start with the sample, we start with a question. Okay, so with a confidence interval, we start with a sample and we say, what does this say about the population? When we do a hypothesis test, we start with a question, okay, or we start with a claim. Okay, so we start with a claim or a question. So perhaps the question is the mean of the population 48? Or maybe the claim, somebody could claim, so that would be the question. Someone could claim the mean of the population is 48. Okay, and then so we start off with this, and then we gather the data. Okay, then we look at the data. So we begin with this, then we go to the data. Okay, and let's just say we had the same data as before, or whatever it might be. We go to the data, and then we say, the question is, does this data provide evidence against the claim? Okay, so someone claims that the mean of the population is 48. Okay, we go to the data and then we ask, does this data provide evidence against the claim that mu equals 48 or something like that? Okay, so if you start off with a question, you've got to kind of turn it into a claim, and we call these claims hypotheses. So does the data provide evidence against the claim that the population mean mu is 48? Okay. And the way we answer this, okay, and if we use the same data, I think we'll see that the process is very similar. But the way we answer this is we ask, what is the probability of seeing our data if this claim is true? Okay, so we we have data, right?
Yeah, it says this now.
Yeah. Okay, yeah. That's after we made the confidence interval. But in this case, let's pretend we haven't done the confidence interval yet.
Oh, okay.
So we have the data, okay, and we ask this slightly odd question, okay? We ask, if I assumed that the population mean is 48, okay, what is the probability that a randomly selected sample um, will look like the sample that I have? Okay, so for example, in our data from the previous problem, we said we had 9 data points. The standard deviation was, I'm sorry, the sample mean was 45, and the standard deviation was 3. Okay, so if indeed the population mean is 48, the question I'm asking is, what's the probability that a randomly selected sample gives me a mean of 45? Okay. Now, obviously, if the population has a mean of 48, every time I take a random sample, it's going to be a little bit different. Okay. We expect the sample means to be close to 48. That's what the central limit theorem tells us. It says if the population mean is a certain value and you take random samples, we're expecting to get sample means close to the population mean. And here I'm getting a sample mean that's 45. Okay, so that's 3 units away.
Plus or minus?
Oh, so we're pretending like we haven't done any confidence intervals. Okay, so we're gonna just so here we're so if the population mean is 48, my sample mean is 45. That's a difference of 3 points, and I'm asking, can a random sample differ from the population by 3 points? Or is the fact that I'm getting a difference of 3 points from the mean, is that an indicator that this is not quite true about the population? Okay, so I'll do another example here that might make sense. Okay, so we're saying, so essentially, if mu is equal to 48, if mu really were 48, then I expect y bar to be close to 48. Okay, I expect y bar of a randomly selected sample to be close to 48. Okay, my y bar is 45. Okay, is the fact that it's 45 enough to convince me that this property of the population is actually wrong? Okay, my y bar, my sample mean, is only 45. Okay, does this provide evidence that mu is not 48? That's what I want to know. Okay, and so the question I'm asking is, okay, if it really were 48, could a random sample produce a sample mean of 45? Well, if it's random, sure, almost anything is possible. But the question is, well, how likely is this going to happen? Okay, what's the probability that a random sample gives me a mean of 45?
That you have a normal distribution of the sample.
Yeah.
Improving.
Yeah. So we're gonna basically this process will rely on that central limit theorem that says things are normally distributed. Okay, but because of the unknown standard deviation of the population, we use S, and we end up using the t distribution, very closely related to the normal. Okay, but so I'm essentially asking, what is the probability that a randomly chosen sample will have a mean of 45 or something even more different from 48? Okay, this is the question that we're going after. Okay. And so if the answer to this question, what is the probability? If the probability says it's quite likely to happen, then we don't have evidence against the claim that mu is 48. On the other hand, if it turns out the probability of getting 45 is really, really, really rare, okay? Because technically anything is possible when you have a random sample, right? It is possible that by random chance you get, you select 100 people and they all turn out to be male, okay? That's very unlikely, okay? But it's possible that you flip a coin 100 times and it lands tails all 100 times. Incredibly unlikely to happen, but technically possible. And we want to know, how likely are we to get 45 if the mean is actually 48? If it turns out to be quite likely, then we got no reason to doubt 48. If it turns out to be quite rare, then we would have reason to doubt 48. Okay, so I'm gonna write that down. Okay, so if the probability that a random sample has a mean of 45, oops, when the population has a mean of 48, if the probability that a random sample has this is high, we have no reason to doubt the claim that the mean is 48. Okay? And on the other hand, I'm going to start off with the same first half here. Okay? If the probability that a random sample has a mean of 45 when mu is 48 is low, this provides evidence, or at least a good reason to believe that mu is not 48. Okay. So let's so we'll get into the math later, yeah, maybe even next week. But I just want to lay the foundations for these concepts first. Okay. Okay. This this thing, the probability that a random sample has a mean of 45 when mu equals 48, this is known as the p-value. Okay, the p-value is a probability is the probability of observing our data or something more extreme if we assume that our, I'm going to write this thing here, that our null hypothesis, and I haven't fully explained what a null hypothesis is yet, okay? That our null hypothesis is true. Okay? The null hypothesis is basically the claim against which you are testing. Okay? So in this case, we're asking what is the probability of observing our data, meaning having a sample mean of 45, if we assume, okay, our null hypothesis is true, if we assume that the population mean mu is 48. Okay, this is a good definition to memorize or learn. I'll put stars around it to indicate that it's important. Okay, the p-value is the probability of observing our data or something more extreme if we assume that our null hypothesis is true. You got that down?
Yeah.
Okay, so let's, I'm going to just kind of do another example. This will be a little bit more of a storytelling one, okay? Let's say you're playing a game, okay, and it's just a simple game of flipping the coin, okay? Flip the coin. And all you do is you call the flip, and if you call it correctly, you win, okay? So if we play the game fairly, what is the probability that we should win for each game that we play? 0.5, right? Okay, if we play fair, we will have a 0.5 probability of winning. Okay. So, let's say, here's it, okay. Let's say you play the game 3 times. Okay, let's say you play 3 times, and let's say you win all 3 times. Okay. And so your friend that you're playing against suddenly accuses you of cheating. Says, hey, I think you're cheating, okay? Or your opponent, whoever, maybe not a friend, if they're going to accuse you of cheating. Your opponent says, hey, you are cheating. Okay? And what would your defense be? You'd say, I just got lucky. Okay? Your defense? It was just luck. Okay? And we can see, well, could you win 3 games out of 3, 3 games out of 3 just by luck? Okay? So we ask, what is the probability of winning 3 games by sheer luck? And we would say, okay, well, that's going to be 0.5 times 0.5 times 0.5, right? So we get 0.125, or 1 out of 8. Okay? So essentially, 1 out of 8 people playing this game will win 3 games out of 3 just by random chance or luck alone. Okay, so 1 out of 8 people will win 3 games by random chance alone. Okay, or we might call that luck. And so 1 out of 8, that seems like it's not a high probability, but it's not very low either. Okay, it's not a very low probability. So we can't disregard this possibility that you won the game just by luck alone. Okay, so this is not a trivial probability. So we do not want to discount the possibility that you won on sheer luck. Okay. However, does this prove that you weren't cheating at all? No, it doesn't. Okay. All this says is that you won 3 games out of 3. You could have been lucky. Could you have actually been cheating and that's why you won 3 games out of 3? It's also possible. Okay. But so I'm going to write note. This does not prove that no cheating was involved. All it says is that it's quite likely for it to happen by luck alone or random chance alone. So we'll give you the benefit of the doubt and say this doesn't cause us to believe that you are cheating. Okay. The fact that you won 3 games out of 3 is not enough to convince us that you are cheating. Okay. Okay, on the other hand, let's say you play the game 10 times, okay? You play flip the coin 10 times. Okay? And you win all 10 times. Okay? Now, again, for each game, you should win with probability equal to 0.5. Okay? But you won all 10 times. And so your friend again says, or opponent says, you are cheating. Okay? Opponent says, you are cheating. Okay, again, you're going to try the same, I was just lucky defense. Okay? Just lucky. So we can say, well, if you are playing fair, how lucky do you have to be to win 10 games out of 10? Yeah, so we'll figure this out, right? If you play fair, how lucky do you have to be to win 10 games out of 10? Okay? Or this is essentially, we're asking, what is the p-value of this situation? Okay? And again, the p-value, the definition of the p-value, you can turn back in your notes, but it says it is the probability of observing our data, or something more extreme, if we assume the null hypothesis is true. So in our case, our null hypothesis which is written as H0 for the null hypothesis, is that you are playing fairly. Or in other words, probability of a win is equal to 0.5. The alternative hypothesis, if the null hypothesis is not true, we have something called an alternative hypothesis. And that is written HA, and that is we are playing unfairly. And this would be the probability of a win is not 0.5 and most likely greater than 0.5. So we're going to say, if you play, the question asks, if we play fair, how lucky do you have to be to win 10 games out of 10? Essentially, we're asking, what is the probability of winning 10 games out of 10 if we assume the probability of winning is 0.5? That is essentially what our p-value is asking. So the p-value is, in the context of this problem, what is the probability of winning 10 games out of 10 if we assume the probability of winning each game is 0.5. Okay? That's what we did last time, right? We asked, what's the probability of winning 3 games out of 3 if we assume the probability of winning each game is 0.5. Okay, and so the same concept applies here. We're going to do 0.5 raised to the 10, and what's the probability that that's going to? So I do 0.5 raised to the 10, and I get 0.000977.
You round down on that one.
Well, it doesn't matter, but it's essentially 1 in 1024. Okay, so we have an option here, okay? If I inverted this, it's 1 in 1024. So there's 2 possibilities, okay? One, you played fairly, and you happen to be 1 in 1,000 people who win 10 games out of 10. 10 games of coin flip, okay? It's possible. You could be that lucky 1 in 1,000. Or the other possibility is, we don't know what you're doing, but somehow you have made it more favorable for you to win. And that is why you've won 10 games out of 10. Okay? So if you are the opponent, what would you do? Should we give you the benefit of the doubt and say you're the lucky 1 in 1,000? Or should we say, or it's easier to say, I think something fishy is going on here, right? And that's exactly what we do, okay? So technically it is possible that you are just lucky and you won 10 games out of 10 fairly, okay? But it seems more likely that something fishy is going on. Okay, and statistics won't tell you what exactly is going on, but it can tell you that it's quite unlikely to get this result from pure chance alone. Okay, so technically it is possible to win 10 out of 10 on sheer luck. Okay, but it is quite improbable. Okay, it's only 1 in 1,000 chance. So we are ready to kind of disregard this chance. Okay, we will conclude that something fishy is going on. So okay. Does that make sense?
Mm-hmm.
Okay. All right, so let's go back and we'll put this into the context of maybe doing a t-test. Okay. So a t-test is kind of a basic form of a hypothesis test. Okay, so a t-test is a hypothesis test. Okay, and it's used for numeric samples. And we are testing the value of the population mean. Okay, we test values of the population mean. Okay, and so when we set up our hypotheses, for a hypothesis, we always have a pair of hypotheses. We have the null hypothesis, which is H0, and H0 will always have an equal sign. Okay, so this is like the claim that the population mean is equal to something, or okay, so okay, and so in this case, our null hypothesis. So for example, we could say we claim that the population mean is 48. Okay, there's always an equal sign in the null hypothesis. And then the alternative hypothesis looks exactly like the null hypothesis. The alternative is almost exactly like the null, except we get rid of the equal sign and we put in a not equal sign, a greater than sign, or a less than sign. The equal sign with either the not equal sign or greater than or less than sign. Okay, so if this is our null hypothesis, then a suitable alternative would be almost exactly like that, except instead of the equal sign we put in a not equal sign. Okay, or I could put in greater than or less than, whatever we want to do. And then we go through the same process and we ask, if the null hypothesis indeed is true, if the population mean is 48, then I expect my sample means to be around 48. And if that's the case, what's the probability that I get a sample where the mean is 45? Or what's the probability that I get a sample where the mean is 47 or something like that? That's what we're asking. And if that probability is high, we have no reason to doubt the null hypothesis. And if that probability is low, that gives us reason to doubt, or gives us reason to reject the null hypothesis. Okay? And so I'm going to kind of be repeating this over and over and over again, but this is the foundation for hypothesis testing. So let's do an example like the one we looked at the beginning. Okay, so someone says, I think, I don't even know what our population is, but I think the mean of the population is 48. Okay, so someone claims this. And so let's test it. Okay, let's test this claim. So we set up a pair of hypotheses. So our null hypothesis in this case is that it's always, we just have to put an equal sign. The alternative will be that mu is not 48. Okay. We take a look at our data. Okay, and I'm going to use the data that we had earlier. N is 9, y bar is 45, and the standard deviation is 3. Okay. So now we're going to calculate the p-value. Okay, so we want to find the p-value. What's the probability that our data looks like this if the null hypothesis is true? Okay, and so to do this, we find something called a test statistic. And the test statistic is always in the form of what we observe minus the value in the null divided by our standard error. And because it's the t-test, our test statistic is t. Okay. So in our case, the value in the null is 48. Okay. And the value we observed for our sample had a mean of 45. So there is a 3-point difference between what we observed and what the null hypothesis claims. Okay. And we want to know, is that 3-point difference large or small? And to decide if it's large or small, we compare that to our standard error. The standard error in this case, with s over the square root of n, when you have one sample, it's s over the square root of n. So it's going to be 3 over the square root of 9. I get a standard error of 1. Okay, so coincidentally there's a bunch of 3's in this thing, but okay, and so my test statistic is 45 minus 48. I get negative 3 over 1. I get a test statistic of minus 3. Okay, so the fact that I observed 45 puts me 3 standard errors below what I expect. Okay, so no longer it's just 3 units. Our standard error happens to be 1 unit, and so I'm 3 standard errors. So this actually gives us a better perspective now, right?
Does that tell us between negative 3 and positive 3?
Yeah. So, when it was the normal distribution, we said almost everything is within 3 standard deviations, right? 99.7. And so that gives us an idea that 3 standard errors is pretty far from the mean, okay? Now, technically, it's not 99.7 anymore because this is the t distribution and we have that compensation factor, okay? So what we have to do is we actually go to the t table, and how many degrees of freedom? I have 8 degrees of freedom, right? I have a sample size of 9. My degrees of freedom is n minus 1. I have 8 degrees of freedom, okay? And so the way our t-table works is we look up the test statistic that we found. I found a test statistic of -3. It's symmetric, so we can just ignore that negative sign. And I'm going in the row for 8 degrees of freedom, okay? And I'm saying, okay, between what columns would 3 fit, okay? So the number 3 fits in between the column for where it says 2.896 in that row of 8. Can you see that? Yeah, let's see. I'm going to draw a straight line here. Okay, so I've got 8 degrees of freedom, right? So I'm going in this row, and I see that 3 fits in between 2.896 and 3.355. So 3 fits in between there and there. Negative, the value 3, because I'm 3. My test statistic is 3. Okay, and so what that tells me, so my test statistic ends up here. This tells me that my tail probability, okay, the column heading says tail probability, okay, so that says my tail probability is going to be between 0.01 and 0.005, okay, because 3 is in between these two columns, so my tail probability is going to be between these two values. Okay, so my tail probability is between 0.01 and 0.005. Okay. And so this is essentially my p-value. Now, I have to bring up a rule here that says whenever you have a not equal sign, the resulting p-value ends up being double your tail probability. And the reason for this is that because my alternative says my null claims that mu is 48, and my alternative says I don't think it's 48. The alternative doesn't claim whether it should be more than 48 or if it should be less than 48. So the fact that we got 45, which is 3 lower than 48, that's interesting. But we would have also been interested if we got 51, which is 3 more than 48. Okay, so it's interesting to us if we got something smaller. It's interesting to us if we got something larger. In certain cases, we're only interested on one side. But in this case, we're interested if it's too small or too big. And so because of that, the idea of being at something more extreme, okay, we ended up down here at 45, okay? But it would have also been interesting if we ended up here at 51. And what the table says is that the area in this tail, the tail probability on one side, this area is between 0.01 and 0.005, okay? And because it's symmetric, that means the same applies over here. This area is going to be between 0.005 and 0.01. I don't know why I changed the order there. Okay.
You said it doubles?
Yeah, so if you look at my picture here, okay, from the table, this t-table that I'm looking at, we know that 3 is between here and here, and so my tail probability is going to be between there and there, right? Between 0.01 and 0.005. That's what I've got. So when I draw my picture, I know that these two tail areas are between 0.001 and 0.005. So I want to know what's the probability of getting something like my data, in this case 45, or something more extreme, so that means even less than 45. But it also means being up at 51 or more. So I'm looking at what's the total probability in both of these tails. So the total area in both tails is between, and I'm going to say between 0.02 and 0.005 times 2, which is 0.010. Okay? And this is my p-value. I'm going to say my p-value is between 0.0, I'm going to change the order so it's least to greatest, 0.01 and 0.02. That's what I'm saying. So now we go back to our original question. And the original question is, if the mean is truly 48, what's the probability that a random sample ends up having a mean of 45? That probability, the probability of that, something like that happening from random chance alone, is between 1 and 2%. Okay? So now we have to make a choice. Do we say, okay, well, it happens between 1 and 2% of the time, so I'm going to say it could have been a result of random chance? Or do we want to say 1 and 2%, that's pretty rare. It seems pretty rare. So I'm more willing to say it didn't happen by random chance, and that this claim that the mean is 48 is actually wrong.
It's like an outlier out there. It could be.
Yeah, so I don't know if you have an opinion, but so the general consensus that has built up over time is that if it happens by random chance less than 5% of the time, we're going to say, probably my null hypothesis is wrong. I'm going to conclude that my null hypothesis is wrong. And the rule of thumb is also that if it happens more than 5% of the time by random chance, then we won't reject the null hypothesis. Now this is a loose rule of thumb, and technically you could say 10%. If it happens 10% or less, then we'll reject, and it all depends. And I'll get into the details of this next week, but this would be the conclusion that we draw in this case. So the rule of thumb right now is what we call a significance level of 5%. And what we say is that if it happens by random chance less than 5% of the time, we will conclude that the null hypothesis is wrong. Now keep in mind that you're going to incorrectly conclude that the null hypothesis is wrong 5% of the time, because 5% of the time you're going to get something that happens by random chance 5% of the time, right? Mm-hmm. So you risk incorrectly rejecting the null hypothesis 5% of the time. But you're essentially saying I'm willing to take that risk. 5% is small enough that I'm willing to take that risk. Okay. And on the other hand, if it happens by random chance more than 5% of the time, we will not reject the null hypothesis. Okay? But also keep in mind that this does not prove that the null hypothesis is true. It just says our data could be a result of random chance. Maybe it is a result of random chance, maybe it's not. But we don't have enough data for us to conclusively say that it's not a result of random chance.
I remember going back to looking at the p-value, I think in one of the earliest chapters, there was kind of like a, is that what we're referring to in this? Or is that just...
So there's probabilities, okay? And when we dealt with the binomial, in statistics we have p show up in so many things, and the p-value takes on a very specific meaning in the role of hypothesis tests. But you're right, when we had binomial problems, we had something called p. And, p always stands for probability of some kind, but it's just, when it comes to a hypothesis test, we have a very specific meaning for the p-value. And it's a probability, but it's a probability of the data if we assume the null hypothesis is true. And so when we say p-value, I'm kind of distinguishing that from all of the other uses of p. Okay, but yeah, you're right.
And that doubling of the...
Doubling of the tail area only applies when our alternative hypothesis has a not equal sign. And I'm going to get into all of the rules and the nitty-gritty. But I want to lay this foundation down for the mindset that we have for hypothesis tests. We want to make sure, we always set up the claim, whatever it is, we always set up an equal sign in the null hypothesis, okay? Because the null hypothesis, we set it up almost in hopes that we can reject it, okay? And so you can reject a specific claim that something equals this exact value, okay? But if you set up your null hypothesis in such a way that it's just very vague, you say, I don't think it's 50, okay? If you say the null hypothesis isn't 50, the only way you can reject that null is if you can prove that it is exactly 50, okay? And that's not possible unless you look at the entire population. So we always set up the null hypothesis in a way that we can reject it, and that requires using an equal sign. But yeah, and then we always ask the question, what is the probability of getting this data, or something more extreme, if we assume that null hypothesis is true? Okay. What's the probability someone wins 10 games of the coin flip game if we assume they played fairly? That probability is quite low. So we're going to say, you know what, I've got a pretty good reason or a pretty good hunch to say you haven't been playing fairly. Okay. On the other hand, winning 3 games, we ask, what's the probability that someone wins 3 games if they've been playing fairly? Well, that happens 12% of the time, 12 to 13% of the time. It's not that small, so it doesn't prove that you're playing fairly, but it's certainly not enough to convince us that you have been playing unfairly. Okay, and that's the mindset that we're using for hypothesis tests. And so next week we'll get into all the details of how the test is run. But that's that.
That's it.
And thanks for coming, and thanks for being my attendee. And those of you who are watching online, I hope you were able to follow along. If you have any questions, don't hesitate to send an email. We'll go over this again next week in class to make sure everybody understands. All right, great. Thank you.